Swayam Prabha. Digital India. Educated India.
Okay, so you don't have to look at the transformation law for these four components if you don't want to. Most of the time you just need to look at contravariant four vectors. But sometimes it's useful to write down the product of G with a contravariant four vector and define that as what is called a covariant four vector. That is these W's with lowered indices. Okay. So let me show you an example of where this is useful. So consider two contravariant four vectors, B mu. Let's call it A mu and B mu. And let's consider the dot product of these two four vectors. So the dot product is a Lorentz invariant quantity. So let's write down this dot product. So the dot product is A transpose dot G dot B in matrix notation. So this is A dot B is this. And in index notation, we'd write this as A mu G mu nu B nu. Okay, again, the index mu is summed over and nu is summed over. Okay. Now, if you look at this quantity is exactly what we called, we can define a covariant four vector, which we write as C mu, which is G mu nu B nu. Okay, which is, so that we can write this as A mu C mu. So the dot product of A and B is related to a simple product between A, which is a contravariant four vector, and mu and C mu, which is a covariant four vector, which is derived from B. Okay. So when taking these dot products, sometimes it's convenient to switch from contravariant four vectors to covariant four vectors in such a way that you can write this dot product very simply without explicitly writing the matrix G. One other thing that I'd like to point out is typically when you go from the contravariant four vector to a corresponding covariant four vector, you typically do not change the letter that describes this contravariant four vector. So conventionally what you would do is, if I write down B mu, this with a lowered index, this is related to B mu with an upper index through this transformation. Okay, so this is the corresponding covariant four vector that corresponds to this contravariant four vector. And so the dot product of A and B is just written as A mu B mu, which you can also show can be written as A lower mu B upper mu. Okay, where this is the covariant four vector corresponding to the contravariant four vector A mu, and B mu is the contravariant four vector corresponding to this covariant four vector B mu. Okay. There's a one-to-one correspondence between the covariant four vectors and their contravariant four vectors. They're just related through the metric G. Okay, so to be concrete, let's take A to be CT X, Y, Z. And let's consider A dot product with A. So A dot product with A is A transpose dot G dot A, which you can write as CT square minus X square minus Y square minus Z square. This is the space-time interval. But you could have also written this in terms of A mu A mu, where A mu upper is CT. I can think of it as this column vector, and A mu lower I can think of as actually, let me just write it this way. It doesn't really matter how I choose to write it, but let me write it as A lower mu, A upper mu. A mu we can write as CT x, y, z, and a lower mu we can write as CT minus x minus y minus z. And it's easy to see what the dot product is. The dot product is then just multiplying this row vector with this column vector. Okay. And this row vector was constructed from the column vector by multiplying the column vector by G, where G is the matrix with zeros everywhere else. Okay. So in this way, we see that the index notation is really quite convenient when we talk about dot products. Now, this seems like overkill when you have only one index, but the next thing that we'll do is we'll talk about tensors, which are objects which have multiple indices, and there we'll see that the use of covariant and contravariant notation is actually extremely useful. So the next thing that we'll talk about is the concept of tensors. So before we talk about tensors in special relativity, it's useful to go back and talk about tensors that we're familiar with, maybe from classical mechanics. So let's talk about the moment of inertia tensor in 3 dimensions, 3 spatial dimensions. Forget about time. Moment of inertia tensor. So the moment of inertia tensor is defined as, suppose you have a distributed mass, and we want to find the moment of inertia about some point. Okay. Then the way we define the moment of inertia is we take a small mass element which is located at some vector x bar, and we sum over each mass element by weighting it by, let's say, its x position in the ith direction. So I goes from 1, 3, and its x position in the j direction. Okay. And this quantity is what we define as the moment of inertia tensor after we sum over all these little mass elements. Okay, so we sum over the entire, all the mass elements of the body. And this quantity defines what is called a moment of inertia tensor. Okay, and this is useful when we compute, for example, the energy of this object when it's rotating about some axis, the rotational energy of the body, or when we're trying to compute, let's say, the response, the angular acceleration of this body in response to some kind of torque which is applied, which is trying to rotate this object. Now, you can clearly see that the components I, j depend on your choice of axes x, y, and z. Okay, so if I choose a different x, y, and z, so x, y, and z, then I would have to rotate my x coordinates, and therefore I would have to correspondingly transform the moment of inertia tensor. Okay, so we want to know, how does the moment of inertia tensor transform under a change of axes? Okay, or what is the dictionary for transformation of the moment of inertia tensor under rotations. Okay. Now we know how the x is transformed. So x transforms by a rotation operator, a rotation matrix multiplied by x. In index notation, we don't use upper and lowered indices for rotations. Okay, that only comes in when we talk about space-time transformations. We use, in index notation, we would say that x prime I would be Rij(x). Okay, this would be the transformed x coordinate. Where a typical rotation matrix, let's say a rotation about the z-axis by an angle theta, would look like this. Okay, and so given the rule for how x transforms, we can figure out the rule for how I would transform. So the rule is, if we have Iij, which is summation over the mass elements times xi, xj. Now the mass elements don't transform under rotation, so that's important because we only need to transform the xi's. So under the dictionary, after we make a rotation, we would get the new matrix or the new moment of inertia tensor I prime ij, which would be summation over dm x prime I, x prime j. And in index notation, again, we can write this as r I, I'll just use a different index here because j has already been used. So this will give us RIL. So remember, the summation is not over indices. The summation is over masses. Okay, the summation is over mass elements. So RIL XL. So I'm actually going to drop this summation because I don't want you to get confused. So there is a summation over mass elements which we're not going to worry about, and we'll now write the x prime I as RIL XL, and there's an implicit summation over L over here, and then there's RI or RJ K X K. Okay, and there's a summation over K. So if I write this out, I can write summation over K, summation over L, and there was previously a summation over the masses, and I can interchange the order of these summations. Okay, and I can do the summation over masses first and then do the summation over the indices K and L. So when I do that, I write this as summation dm. Sorry, write it in this way. So RIL RJK summation over masses XL XK. Now the reason I can take the rotation matrices outside of the summation over masses is that the choice of rotation matrix has to do with the choice of our axes, okay, which has nothing to do with the distribution of the mass itself. Whereas the positions of the mass in one coordinate system certainly do depend on which mass element I'm talking about, so I cannot pull these x's outside the summation. Okay. So now when I do this, I get summation over K, summation over L, RIL, RJK, and this quantity is nothing but our old moment of inertia tensor, which is ILK. So the transformation rule for the matrix or for the moment of inertia tensor I prime looks like this. Okay, if this is in index notation, but we could write this in matrix notation. If we think of I prime as having two indices, I and j, we can think of the matrix I prime as being related to the matrix I by the following transformation. This looks like R dot I dot R transpose. Okay, this is in matrix notation, but this is in index notation. Okay. So you think about the matrix I of the moment of inertia tensor. Imagine hitting it on the right or on the left by a matrix R, and hitting it from the right by a matrix R, but I have to transpose this matrix when I hit it from the right. Okay. Now you could imagine constructing more complicated objects hypothetically. Okay, we don't know what physical quantities they describe, but in principle we could construct something like xi, xj, xk. Okay, so our previous object that we constructed had only two free indices, I and j. So this is called a rank 2 tensor. But something like this is called a rank 3 tensor. Okay, so this is a rank 3 tensor. And we can ask, how does this object transform? And in index notation, again, it's very easy to see how this transforms. So it would be x prime I, x prime j, x prime k, which would be related to the old quantities by ri a, r j b, r k c, x a, x b, x c. Now, this is a more complicated object to look at in anything other than index notation. So if I want to imagine what this object is, I have to think of it as a 3-index object. So unlike a matrix, I have to think of this as a cube of values with, let's say, the index A describing the rows, an index I describing the rows, the index J describing the columns, and k describing the depth. Okay, and this transformation rule is effectively telling me that I have to hit it with a matrix R from the left, a matrix R from the right, and a matrix R in this perpendicular direction. Okay, so it's obviously much more complicated to describe than the simple laws of matrix multiplication that we've written down before, but it's much easier to write down when we write it down in index notation. So this is where the power of index notation comes in. Okay, for rank 3 or higher tensors, it's much easier to write the transformation rules using index notation. Now you'll see that the way we've constructed this, I runs from 1 through 3, j runs from 1 through 3, and k runs from 1 through 3. So the object that we've constructed has 27 components. Okay, for every independent choice of I, j, and k. So in general, we can write down, and the way we constructed this this object, okay, we can write it as a single object with indices I, j, k. Okay, just as we defined the moment of inertia tensor as an object with two indices I, j. Now, the way we constructed Ij, or this rank 3 tensor over here, is we took what is called a tensor product, okay, of 3 vectors, or 2 vectors when constructing the moment of inertia tensor. But you can intrinsically assume that there are objects which are not constructed as tensor products, which obey this transformation rule. That is, I don't know what this object is, or I don't know how to construct it from vectors, But I can tell you that the transformation rule for W prime is that it's related to the components of W, the 27 components of W, by some kind of law like this: RIA, RJB, RKC, where there's a summation over A, B, C. Okay, and similarly, there's a transformation rule for I, which relates it to IAB, that is the old I, okay, RJB. Okay, so this is a dictionary of rotations of a new set of objects which we call tensors. These are rank 2 tensors, and these are rank 3 tensors. And the generalization of this is to construct a rank n tensor, and this would transform in the following way. There would be matrices R Ri1 J1, Rin Jn, which transform the original W and give us the new W prime. So this gives us the most general dictionary of how different objects can transform under rotations. Okay? And now we just generalize this to special relativity. So in special relativity, which involves not just rotations, but boosts, Lorentz boosts, we can take tensor products of 4 vectors. So if we have 4 vectors, V mu, W mu, and X mu, okay, so imagine some 4 vectors, we can construct a tensor product object V mu, W mu, W nu, X rho, and you see that mu takes 4 values, nu takes 4 values, and rho takes 4 values. So this object that we've constructed has 4 into 4 into 4 components. Okay, so that's 64 components, and this is called a rank 3 tensor. A mu nu rho. And we don't have to start with 4 vectors. We could imagine that there are just objects A mu nu rho, which are intrinsically what we call rank 3 tensors. And we say that the dictionary for transformation of these rank 3 tensors would be something like this. So if I want to know what this is in a primed frame, so A mu nu rho, this would be related by our transformation matrix lambda. So lambda mu alpha, lambda nu beta, lambda rho gamma, A alpha beta gamma. So the components A alpha beta gamma are the components of A in the old reference frame S, and there's an implicit summation again over alpha raised in lowered indices, beta raised in lowered indices, and gamma raised in lowered indices. Okay, and this is the transformation law, which is again simple in index notation. And so the most general rank n tensor that I can write down is something like this. So A prime mu1 to mu n. This is a rank n tensor, and this transforms in the following way: lambda mu1 nu 1, lambda mu2 nu 2, lambda mu n nu n, A nu 1 to nu n. Okay, so this is the same rank n tensor in frame S. This is the same rank n tensor in frame S prime, where the frames S and S prime are related either through a Lorentz boost or a rotation. That is, they're related by any element of the Lorentz group, any matrix lambda of the Lorentz group. So in the special case where the object A has no indices, okay, so an object with no indices, this object will be the same in the frame S prime. Okay? So such an object is called a Lorentz scalar. Okay, so things like the space-time interval that we've seen, for example, are Lorentz scalars. Okay, or the speed of light is a Lorentz scalar. It doesn't transform from one reference frame to another. Whereas things that transform, we have now derived the most general dictionary of how things can transform. Things can transform either as rank 0 tensors, which is to say they don't transform. They can transform as rank 1 tensors, which is to say that they transform as contravariant 4 vectors. They can transform as rank 2 tensors, rank 3 tensors, and so on. Okay, you can go on constructing higher and higher rank tensors, and you can get dictionaries for the transformations of these tensors. The challenge is to know what objects transform like which rank tensor. Okay, that statement is the non-obvious statement. How different things, which rank tensor do these objects transform as? So we had to derive, starting with the fact that the speed of light is constant for all observers, we figured out that this quantity transforms like a 4 vector. Okay, which we called the position 4 vector x. And all the other transformation laws were derived from the transformation law of this 4 vector. Okay, so all our other transformation laws were derived transformation laws. But in some cases, you might just have to guess what the correct transformation law is, and nature will tell you whether this is the right transformation law for the collection of objects that you're trying to describe. Okay, so it's not always possible to derive transformation laws. Sometimes you have to guess what the correct transformation law is. But among the possible guesses, everything should be expressible in terms of tensors of some rank. Okay, either rank 0 scalars, rank 1 4 vectors, rank 2 tensors, and so on. So this here is the most general dictionary of Lorentz transformation. Okay, so we will see specific examples of different objects that transform in these more complicated ways later on. And finally, I'll just show you one more thing, which is supposing I have a rank n tensor of this form. It's possible to define, so here all the indices are upper indices. Okay, so these are called contravariant indices. And it's possible to define a similar object where some of the indices are lowered. So for example, if I lower the kth index but keep the other indices raised, this can be related to the original A by something like this. So G mu k nu k a mu 1, and wherever I was supposed to have the mu k index, I put in a nu k index. So this lowers an upper nu k index to a lower mu k index. Okay, so this is in the frame S. This is also an object in the frame S. Okay, this is not a transformation of reference frame. This is just defining an object which is made up of the old collection of objects that we had. Okay? Just as for a 4-vector, a contravariant 4-vector, we can rearrange the components slightly to get the covariant 4-vector. And the lowered indices transform with this matrix. This is the transformation for lowered indices that we've seen for contravariant indices. And lambda is the transformation rule for upper indices. Okay. So sometimes you get what are called mixed tensors with a mix of covariant and contravariant indices. Okay, this will be useful when we start taking dot products. So for example, we could take a dot product of a tensor. So again, suppose we want to take a dot product of the kth entry of this with a vector v alpha. So what we would do is we would multiply by g and we would sum over mu k and alpha. Okay, so it's useful to so this is some kind of special dot product where we're taking a dot product of v with the kth entry of this tensor. Okay, so this is like if we have a moment of inertia tensor in rotations and we take a dot product with, let's say, the angular velocity omega about the I-axis and a dot product with omega about the j-axis. This would be related to the energy, okay, of a rotating object. Okay, so that's why you might want to consider these kind of dot products. And so this kind of dot product can now be easily written by using mixed tensors. So with mixed tensors, you would write a mu1, and then in the location of the kth index, I lower the index and I write v with an upper index. Okay, so this is a partial dot product of this tensor with a contravariant 4-vector. So that's where these mixed tensors can be useful. Now, two more things that I'd like to tell you is one is when you have a tensor, let's say with all upper indices like this, it's also possible to take a dot product of two indices, let's say the ith entry and the kth entry. Okay, so you can take a dot product by simply multiplying by g mu I mu k and then doing the summation over mu I and mu k, which is implicit here. Okay, so what this would do is if you have a rank n tensor, taking the dot product of two indices lowers the rank so that the new object that you get is a rank n minus 2 tensor. Okay, you can check that this new object would transform as a rank n minus 2 tensor. So it's only the number of what are called free indices, that is the indices that are not appearing in pairs of upper and lower indices which are summed over, but rather the unpaired indices which are free. You're free to choose the values of those. It's the number of such free indices that determines the rank of the tensor. And finally, it's possible if you have two tensors, let's say one of rank n and another tensor of rank m, it's possible to construct a tensor product of both of these, just as we constructed tensor products of 4 vectors. So we can consider the object or the set of objects. So it's a multiplication of just numbers. Okay, so for each value of mu1 through mu n, we take the corresponding component of the tensor A. For each value of nu1 through nu m, we take the corresponding component of the tensor B. And this gives us what is called a tensor product. Okay, and we multiply these two numbers together, and that collection of objects is a tensor product. And you can easily see that the rank of this tensor, this new tensor, is n plus m. Okay, so this gives us some new object that transforms differently under Lorentz transformations. It transforms as a rank n plus m tensor. Okay, you can similarly construct tensor products of tensors which are mixed, which have mixed covariant and contravariant indices, which I won't write down, but it's an easy generalization of this idea of tensor products. So let's summarize what we've learned today. The first thing that we did is we learned how to write down 4 vectors using what is called index notation. And we learned how to write down dot products in this index notation. And we saw that it's useful when we talk about dot products to talk about not just conventional 4 vectors, which we think of as contravariant 4 vectors, but to talk about what are called covariant 4 vectors, which are not different objects, but rather the same object written differently. Okay, and then we talked about how using the ideas of index notation, we can generalize, we can write down a general product of 4 vectors, or what is called an outer product of 4 vectors, to define what is called a tensor product. Okay, and this tensor product can be generalized to an arbitrary number of vectors. Okay, and we have a collection of objects. Oops. So we have a collection of objects. So v1 through vn, a collection of 4 vectors, and each one we choose a different index for, and depending on our choice of indices, that gives us a different number when we multiply them out. And the result of all these numbers is what we call a tensor product. Okay, and this would give us what is called a rank n tensor. And we saw how these rank n tensors would transform. Okay, so we wrote down a transformation law for these rank n tensors. And then we conjectured that there are objects which do not have to be written as tensor products, but simply exist as tensors of rank n. Okay, so you don't have to construct them from taking tensor products of vectors, but maybe they're just objects which have the same transformation properties as these tensor products, and those are what we call tensors. And the transformation law for tensors we wrote down looks like this. So in the frame S prime, the tensor T is related to the tensor in frame S through these transformations in index notation, where T is the tensor in frame S. Okay, and we also saw that we can construct mixed tensors. That is, we can raise and lower the indices of tensors using the metric g. Okay, so if we use a lower g, we can lower the indices of t, and we can even take dot products of tensor indices. Okay, so we can define what are called mixed tensors, which have some upper indices and some lower indices. And we also saw that we can take tensor products of tensors to construct new tensors of higher rank. Okay, now tensors will be very important when trying to write down any physical law, such as Newton's laws or Maxwell's equations, because if we can properly identify what combinations of objects transform as tensors of a particular rank, then we know the transformation properties of that collection of objects. Okay, so just as we discovered that CT, X, Y, Z transform as a 4-vector, and from this we could derive various other 4 vectors such as u mu, the velocity 4-vector, and partial mu, the derivative 4-vector. Just like this, suppose we knew the transformation laws for certain other objects which transform as tensors. It need not be true that we can derive that these objects transform like tensors. We have to kind of conjecture or guess. But once we correctly identify the objects that transform as tensors, we know how they would look to one observer in frame S and how they would transform to an observer in frame S prime. Okay, so what we have found in this class is the most general dictionary. Okay, and this most general dictionary just requires us to identify what the tensors are when we talk about physical quantities, and how that will automatically tell us how they transform from one observer to another. And then we'll see in the next class that when we write down physical laws, okay, the physical laws should when they're expressed as an equality, so the quantity on the left hand side of the physical law and the right hand side of the physical law should both transform in the same way. That is, on the left hand side, if I have a particular tensor of rank m, the right hand side should also be a tensor of rank m. Okay, so this will be the condition on physical laws to obey the principle of special relativity, because only when they transform in the same way, the left hand side and the right hand side of a physical equation, law equation, only in that case will the laws respect the transformations of special relativity. That is, they will look the same to an observer in one reference frame as they do to an observer in a different reference frame. So if I were to transform this law from frame S to frame S prime, this would look like, let's suppose it looks like T mu1 through mu m, and this is T or some other tensor, A mu1 through mu m. The law in a different reference frame would look like T prime mu1 through mu m, where this is the tensor transformation of the original tensor, and A would look like A prime mu1 mu m. Okay, what is important is that the collection of objects that you've written down over here and the collection of objects that you've written down over here transform in exactly the same way under Lorentz transformations. That is, they should transform like exactly the same tensor or tensors of the same rank. Okay, so this will be a very important criteria for determining the natures of physical laws, and we'll see that Maxwell's equations satisfy this criteria. Newton's laws do not, and they have to be modified appropriately so that they respect the laws of special relativity, okay, or the constancy of the speed of light.